I'm just going to go through a high-level overview of just the full modeling workflow. So how you set up a model, what are the steps and decisions that come into play, and then how it links to this method known as the finite element method. So feel free to jump in with questions if you want. So consider this following simple real-world problem. So let's just imagine we have some component or attachment or plate or something like that. And as part of the design process, before making it and testing it, you just want to model it and check if it's going to break, because it's going to be under high loads, and you just want to check, is your design, I forgot to say about that leak. I really need to tell someone about that. I don't know if people know about that. So you have to check in advance, is this thing going to break? So you're going to do a stress analysis of what you expect the loading to be, and you want to check if it's going to break. Okay. So it's going to be held in some way over here, and then it's loaded, connected to some other component. So maybe the question might be what? Will it play yield or fraction? So the first step in finite element modeling, and in fact all types of modeling, is defining what's known as a mathematical model. So this is something you do in advance of opening a computer or a piece of software. This is something independent of a numerical method like finite element method. This is the concept of look at real life and think, are there any maths equations that might approximately describe what's going on? That's the idea of a mathematical model. So if I look at a spring, you might say, well, that kind of follows Hooke's law, F equals Kx. That's a mathematical model. It's a very simple mathematical model, and you don't need abacus to solve F equals Kx. You can do it by hand, or you can use like Excel to do it or something like that. And so, as we'll see, there's certain types of mathematical models that are suitable to be solved by softwares like abacus. So what is a mathematical model? So for the types of problems we look at, it generally has 4 parts. So it has governing equations, geometry, materials, and load. So regardless of the software you're going to use, you'll always have to follow these steps. So I said at the start, we use a few different softwares, but part of the purpose is when you go out, if you do modeling in your career, you may not be using any of those softwares. So it's important that you learn what are the underlying concepts so that you could just use any software. Because you might not know where the button is, but you know that button exists, and then you'll know how to do it. Okay, so let's start with the governing equation. A little head out of the way. In this case, we're interested in calculating the stresses in the part. So for any problems calculating stresses in solids, we'll always start with the conservation of linear momentum. So that's this equation in steady state form. That's basically a generalization of Newton's second law. So Newton's second law says like F equals ma, or more generally, if you sum all the forces on any piece of material, it equals mass by acceleration. And if that material is not moving, then its acceleration is 0. So that means if you sum all the forces on any piece of material, then it equals 0. So all the forces should balance. So I might just take a quick, I'll just change over maybe to my iPad to remind you a little bit about differential operators. So, share up here. So the equation we saw behind there is a partial differential equation. So we can maybe you remember what they are if you did CCM1, or maybe you're not really sure what they are. So I'll remind you about some of these things. So one of the key things you notice when you see a differential equation is you see the symbol nabla. So nabla represents a differential operator. So it basically just represents ddx, dy, dz. So it's differentiating something with respect to space, spatial coordinates. So you might just say ddx, and x is a vector, which is a spatial coordinates. So nabla is basically a way for us to check how something changes in space. And this is a characteristic of a partial differential equation, that you're talking about things that change in space. So for example, in this room, we can define a bunch of different fields, and fields are quantities that vary continuously throughout the space. So for example, temperature is a field. So I can define the temperature at every point in this loop. I could also define, so that's a scalar. I could also define a vector field, which is the velocity of the air at every point in the space, or something. Or even not the velocity of the air, the velocity of the material that occupies every point. So if I take a piece of the desk, it's not moving, but the air around it has convection tension and stuff. So that's a field, and that's a vector field. So I can use differential operators to operate on those fields. So I can put this nabla in front of t or v for velocity, and I can do different things to get more information about those fields. So there's a variety of different ways they might be used. So first of all, if let's just say t, so I'll use t to represent, actually maybe that's confusing. I'll use s to represent a scalar field. So that's a function of x, y, and z. So like e.g. could be temperature. And then maybe v, and normally in text you would have a bold for representing vectors, and tensors, which are a generalization of a vector. And so I might use v for a vector field, and it's the same, some function of x, y, z, e.g. velocity. And then you can also have tensors. A tensor, you can think of it as a 3x3 matrix, except it has symmetric special properties. So tensor, you can also think of as just 3 vectors. So you can define the stress at every point in the material in your space. So that might maybe not be as natural for a fluid. If you think about in the desks or chairs you're sitting on, at every point you can define a stress tensor, and that represents how the forces are transferring through that material. You can do the same in air, a little piece of air, you can define the stress tensor as well. So one way to think of a stress tensor is it's just 3 vectors. It's like what's the force vector going through the x direction, the y direction, and the z direction. It's just a combination of those. That might be a tensor field. And then all of these can generally be called tensor fields. It's just this one is a second order. A second order tensor, and a vector can be called a first order tensor, and a scalar can be called a 0th order tensor. And then you can have 3rd and 4th order tensors, and you keep going as much as you want. So e.g. stress and strain. Okay, so then let's look at some of the operators. So let's say I can go grad s, so that could be like grad of temperature. So s is a scalar, or maybe I could go grad of v as well. So when I write them like this, this is called the gradient of s. It's the gradient of v, and I could also go grad t, the gradient of t. So the gradient operator, when I write it like that, so I just write nabla and then whatever I'm talking about. I don't have any dots or any other symbols or crosses or anything. That's just a gradient. So that defines how something is changing in space. So when you talk about gradients, I'm not talking about time. There's nothing to do with time here. You could define how something changes in time, like a temporal derivative, but I'm not talking about that. I'm just talking about how it changes in space. So if I said it was 19 degrees on that side of the room, and it just happens to be 20 degrees on that side of the room, I could define the gradient of temperature from that side of the room to this side of the room to be 1 degree per, I don't know, whatever that is, 6 degrees. So it's change per distance. So if I have temperature, that's in Celsius. The gradient of temperature is the change in Celsius per meter. So if I have a scalar temperature defined everywhere in this room at this particular point, if I just look a little bit that direction, let's say that's X, that's Y, and that's Z, or something like that, I can say, well, if I move a little bit in the X direction, the temperature might be a little bit higher or a little bit lower, or might be the same. So I can define at a point, I can define what the gradient in the x direction is of temperature. So the gradient of the temperature in the x direction is saying at that point, what is the rate at which it's increasing or decreasing the temperature in the x direction. So if I say positive x in that direction, it means if that's a positive number, it's increasing the temperature if I go in that direction. And equally, I can define a gradient in the y direction and then gradient in the z direction. So we can see if we have a scalar and we take the gradient of a scalar, that gives us 3 numbers. So if you have a scalar, which is 1 component, you take the gradient, you get 3 components. So this thing is a vector. So equally, if I take the gradient of velocity, velocity has 3 components. At every point in space, I can have a velocity vector. And I could say, well, the x component of velocity and the y component and z component. I can look at each component individually and see how it varies in the x, y, and z. So if I have the x component of velocity at every point in space, that's a field. And then I can see how that field varies in the x, y, and z. And then I can check the y component velocity, how that varies in the x, y, and z, and the same with the z. So that means you actually get 9 numbers for the gradient of velocity. So that'd be a tensor or a second order tensor. And then finally, if you have a tensor which has 9 components, you take the gradient, you get a third order tensor. So it's times 3. So you get 27 components. So for every component of your whatever quantity is, it will vary in 3 directions. So you have 3 numbers for 3 grades. So that'll be a third order tensor. So the thing we can generalize is gradient increases the order. So scalar, you take a gradient, it's vector. Vector, if you get the gradient, it's a tensor. A tensor, you take the gradient, it's a higher order tensor. Very good. So if I take a simple little example, we just draw a little square. So if you imagine in this is a little, I'm looking at a little piece of material in some room or some domain. So that domain might have the temperature defined at every point. So maybe over here it's hot, it might be like 10 degrees or something like that. And starts cooling down. In this direction, it's only 8 degrees. Maybe over here it's 6 degrees. And I'm just picking random points and just defining some temperatures. 4 degrees. So if I'm looking at a box in this entire domain, if I want to know the gradient just inside that box or this little piece of material, how can I do that? So let's say the grad of, it's probably confusing, I'm using T here for a tensor as well. So if this tensor here, I'm going to use S just to avoid any confusion. Let's say S. So this T here is just temperature. So it's just a scalar. So if I want to calculate the gradient just in this little area here, this little box, what might I do? Well, I could just say, look at the temperature on the left and look at the temperature on the right. And then I could just say that the gradient of the temperature in the x direction is the temperature at the right minus the temperature at the left divided by the distance. Okay, so just look at how much it changes. And equally, I can define the gradient of the temperature in the y to be maybe the temperature at the top minus the temperature at the bottom. So T top minus T bottom over delta y. And we can say delta x is the distance in that direction and delta y is the distance in that direction. So as I let these delta x's, delta y's go down smaller and smaller into a point, then you approach the gradient at a point. So you can define the gradients at a point as the limit of these points. So then I can define my gradient vector here in x and y. It's 2 meters. So what this gradient is, whenever you see the gradient, something it's measuring the rate of change in space, not in time. So it's how something's changing in space. So why do we care about the gradient of temperature, for example? Well, heat flux Q is equal to minus K times grad of T. So grad of T is a vector. K is the thermal conductivity. And now we have a minus. So current thermal conductivity, typically it's scalar. It could be actually a tensor as well, if it was an isotropic or anisotropic material. And then Q is a heat flux vector. So the sizes have to add up on the left and right. So if you have a vector on the right, you have a vector. So that basically says that if the material is getting hotter, if you have a positive gradient in the x direction, so left is cold, right is hot, that means it's getting hotter from left to right, then heat flow or heat flux is proportional to that temperature gradient, but in the opposite direction, it's minus. So heat energy flows from hot to cold. So if you have a positive temperature gradient, so from cold, say it's cold here, and then the gradient is positive going in this direction, it means you're getting hotter and hotter and hotter in the positive gradient. So that means heat flux Q flows in the opposite direction. So if we were to draw, pick some other color, so then maybe in this case, you might get Q flowing in that direction, that'd be your QX, and maybe a QY in that direction if it was hotter in that direction. Actually, based on the temperatures I've drawn, it would be in the other direction. So I said it's hot, getting colder, colder, colder. So the heat flux vector will be generally in this direction, like heat flows from hot to cold. So if I calculate the gradient here, I'll get minus numbers in the x and minus numbers in the y, because it's getting colder in the x and colder in the y. So very good. So that's this gradient operator. So it's easier to understand the gradient operator, I guess, thinking about a temperature or something like that, and a scalar. And when you think of the gradient of a vector, maybe it's more confusing, but just think of it in terms of its components. Independently, the x velocity is just a scalar that may increase in one direction, but at the same time, the y component increase. So the x component velocity can change in the x, y, and z directions, the same as the y. So that's why you have all these extra numbers. So I could equally draw this image with all these velocity vectors all over the place, and I can get the gradient of velocity as well. Very good. So that's the gradient. But what about the divergence? So if Q is a vector, e.g. heat flux, and sigma is a tensor, e.g. stress. So if you take the divergence of a vector, you get a scalar. If you get the divergence of a tensor, you get a vector. So gradients increase the order of what you operate on, and then divergence decreases. It goes in the opposite direction. And so this thing is a scalar, and this thing is a vector. Divergence or div decreases the order. And how you distinguish a divergence from a gradient is the divergence is the nabla, the upside down triangle with a dot after. That's normally how the divergence is written. So what is divergence? Why do we care about the divergence? Well, both divergence and gradients appear a lot in physical systems. So from physical bonds and conservation laws. So if we think about the temperature in here, if I take any box or like define like a box in space or an area in space, not a box, just any area in space, and I look at the temperature in that space. So I can see that maybe there's some energy flowing in from the left, maybe from the right, maybe some flowing out the top and bottom. So what I can say is if it's reached steady state, that if I just sum what's flowing in and out everywhere, it should equal 0. So all of them should balance. So that's what the divergence said. The divergence is basically defining summing what's flowing in and out of any region of space. That's kind of physically the interpretation of the divergence. So the gradient, the physical interpretation, is just how it's changing in space, but the divergence is physically summing up what's flowing in and out. So if I take another little box here. So if you imagine I define little vectors heat flux vectors. It could be velocity vectors if you wanted as well. And I calculate the divergence of u. What the divergence of u basically is saying is if you go around each of the sides and you look at how much is flowing into across that side. So the vectors will have a normal component and a tangential. So it's only this normal component that causes flow into the box at this point. And it's the same for all the sides. Some sides you might have flowing out, sometimes flowing in. So if it's at steady state, if you sum all of those up, it should equal to 0. So mathematically, the way that's written is divergence of Q that can be written as an integral. So when we write differential equations, we can write them in differential form or integral form. They're equivalent. It's just differential form, which is the first one here. That's at a point, and then integral form is applied to an actual finite volume body, like a piece of material that has a volume. But that can equivalently be written in terms of the surface, summing over the surface. And these are unit normals. And this thing is the areas. So it can be written as, and maybe it's a bit confusing. These unit normals, you can sum around the surface and just take the n dot q, which means the normal component. N is a normal vector. So the normal component of q, so if q has a heat flux in the x and the y, you just take the normal component, so that's the x. So you just say the x here plus the y there, minus the x here, minus the y there. If you sum all of those up, they should equal to 0. And so then you can also see then when we plug it all together, that we have a definition of Q is K grad T. So this is just a steady state energy equation. So you'll often see this div dot grad of something like that. So div dot grad is basically summing around the flow of something in and out of something. Okay, I'm going to jump back. So this divergence of sigma, anytime you see divergence, just think of a little piece of material and you're taking the normal component on it. So sigma is a stress tensor. Tensor is just like 3 vectors. So it's like you're taking the normal component of each of those 3 vectors on the surface. So that actually is just the force. So you're just taking a piece of material and you get the force on the right, which is vector, top, bottom, left, sum them all equals 0. So that's all this says, just a fancy maths way of saying at any point, if you sum all the forces, the surface force equals 0. So that's great, but stress has 9 components or 6. It's a symmetric tensor, so that just gives us 6 unknowns. So that doesn't have to solve anything. So if we can write that in terms of a vector displacement, and this is a vector, this whole thing's a vector. So second order tensor by a divergence, that's a vector. So that's 3 scalar equations. So if we can write this in terms of 3 unknowns, then we can solve it. Okay, 3 equations, 3 unknowns. So we have 3 equations, 3 scalar equations here, but we have 6 unknowns. So we need to rewrite it in terms of 3 unknowns. And what we normally do is we write it in terms of the stress in terms of strain and the strain in terms of displacement. And then we have the whole thing, the only unknown is displacement, 3 displacements. So remember, we haven't actually even got to finite element or anything. This is just the maths. This is before opening the computer. We're just looking at the problem and saying, well, it probably satisfies conservation of forces or momentum. So just in making that assumption, we're ignoring gravity. We're assuming gravity doesn't affect this plate. And we're ignoring the inertia. We're assuming there isn't any accelerations. And we're ignoring maybe temperature effects and lots of things. So we're making lots of assumptions already. If they're wrong, they'll introduce errors. If they're very wrong, they'll introduce a lot of errors. Okay. How do you know if they're good assumptions? Well, as we go on, you may have to come back and then disregard that assumption and include more complexity, see if it changes the answer. So modeling is a very much an iterative process. So that's the governing equations. And next is the geometry. This is the real geometry. You can see it has scratches and bumps on the surface and the holes aren't perfectly circular. So I'm going to make some idealization or simplification of the geometry. I'm going to assume it's maybe perfect circles, certain radii, things like that. So what assumptions? Maybe I'm assuming straight edges, perfect circles, ignoring fillets, maybe ignoring bolts, things like that. Are they good assumptions? Well, you can't say until you understand what the problem is. And you may have to make a first attempt model and see what the answer is, and before you can see if that makes an effect or not. So one way in modeling, which you have to do a lot, is you make a model with and without the assumption and see what effect it has. So it means that when you're trying to model something, in reality, you probably have to make a large number of models to try to understand it fully, unless you have experience in this area and you can sort it out. So we need to decide 2 things then for the material. So remember, there's always these 4 things making any model, whether it's a fluid or a solid or any software. You'll always have governing equations, materials, loading conditions, and geometry. So then the material law. So how do we relate the stress tensor, or it could be heat flux for a heat problem, to the unknown variable, whether it's displacement or temperature. So we have to decide 2 things: what material law, or it's called a constitutive law, to use. So let's assume this plate maybe is elastic. So maybe we'll assume it follows Hooke's law. And then if we say it follows Hooke's law, which could be wrong or not perfect, then we have to pick parameters. These laws will have parameters. So Hooke's law is defined by 2 material parameters, Young's modulus and Poisson's ratio. So if we pick those wrong, we will also have to introduce errors. So we can start with 3D Hooke's law, and it requires 2 parameters. So what other assumptions? Well, maybe we're implicitly assuming the strains are small. It's not like undergoing large strains. We're assuming it's not undergoing plasticity, viscoelasticity. There's no heterogeneity, as in maybe the Young's modulus is a little bit higher here than it is over there. And viscoelasticity, temperature effects. Are they good assumptions? Well, we may have to come back and check and not exclude those. There are other ways to exclude those effects as well. And so loading, so we've done governing equations, geometry, materials, now loading. Well, how loading or boundary conditions? Well, maybe we can just say the displacements are 0 at these points, and we'll apply forces or charges on these sides. This represents some external components pulling this apart in some way. But maybe we should actually draw the bolts. Maybe it's important, the distribution of forces on those holes may be important. Maybe not. It's not clear. So often when you're setting up a model, if it's unclear whether you should include something or not, pick the simplest thing and just get some model that's simple, and then you can check, is this approximately capturing what's going on? And if it's not, then you go back and add complexity. So assume uniform is loading on the right holes. Is that what really a bolt does? Probably not. A bolt, if it was being pulled, will have a high pressure and drop off, and then on the left side of the hole, it will not be in contact, it will have 0. And then 0 displacement, is that exactly correct? Nah, maybe not exactly, but depends on what your goal of your model is. So that's the mathematical model. So once you've agreed all those things, then you can decide, well, is a software like Abacus appropriate for solving this type of a problem? So that's where we come to the numerical model. So this one thing that you should hopefully come away with from this course is the difference in types of errors. So there's something known as modeling errors. Everything we discussed there, all those possible errors are called modeling errors. That's not Abacus's fault. That's just you have set up a problem that doesn't describe reality. So when you define a math simplification of reality, it introduces errors. And once you define that simplification, perfect, straight, clean holes, Hooke's law with parameters, then it's up to a finite element to solve that. And then the finite element method doesn't do that exactly. It also has errors, for example, to do with the mesh. Those are numerical errors. They're unrelated to your assumptions about the real life problem. It's just related to computer methods' inability to solve it exactly. So by approximating a real life problem as a mathematical model, we've introduced many assumptions and errors related to the governing equations, geometry, materials, and logic. So next we'll use the finite element method, or we could use the finite volume method, or finite difference method, or spectral methods, or meshless methods. There's a whole host of different numerical methods that can solve partial differential equations. It's just the finite element method is most commonly used for stress analysis problems to solve this ideal mathematical model. And this will introduce additional errors. So let's go through the errors it introduces. So we'll go geometry, loading, and materials. So this is our ideal geometry, which isn't the real geometry. This is just an ideal one. We're going to split it into a mesh. So if you look here, the little circles aren't captured perfectly for using straight edged elements. So the geometry won't exactly be the same. As you refine the mesh, it'll go towards it, but it isn't exactly. So we can define this mesh to be made up in terms of infinite element. They call them nodes and elements. In finite volume, like when we go to ANSYS state, it looks the same, but they normally call them cells instead of elements, or control volumes. But it's the same idea, and they might just call them points. But a node and an element, so nodes are just the points, the intersections of all the lines, and then elements are just a little triangle, just squares. So notice that the geometry may not be captured exactly by these lines. So what does the finite element method do? So you can't see the shading very well here, but these 6 elements are shaded. So what the finite element method does is for every node, so let's say we go to this red node, it tries to apply this equation. So let's imagine we have subbed in, I haven't done it here to keep things concise, you sub in an expression for stress by Hooke's law, it'll be in terms of an unknown displacement. So this is a vector equation, so 3 scalar equations, and there's 3 unknowns, 3 vector displacements, okay? Or three displacement components. So this equation is 3 equations and 3 unknowns. Mathematical unknown functions, that is, displacement functions. So what the finite element method does is it basically takes a node, and then for the elements around it, it applies this equation. So it tries to rewrite this maths equation in terms of algebraic equations. What are algebraic equations? They're just like simultaneous equations. So it tries to rewrite this function as some number multiplied by displacement here, plus some number by here, plus some number by here. So that's what it does, the finite element method, and the finite volume method, and the finite difference method, and all those methods, they all just do that. They just try to write it by some number like this, by this, by this. And these A1s, A2s, A3s, they call them coefficients. Where they come from, that's the derivation of the finite element method, and that can be a whole lot of fun in the maths of getting into differential calculus. But in essence, these A's, they're typically vector or tensors. So that might be a 3 by 3 multiplied by this, 3 by 3 multiplied by this. So this represents a vector equation. And if you have 7 nodes in this equation, you have 3 equations, and then you have 7 unknown vectors. So you have 21 unknowns in this case. So for it to do this, and we won't go through the details here, but I will in some other slides, it makes some assumptions about how the displacement varies across these elements. So if you've heard of shape functions and you know the details of them, it's just a fancy way of saying, well, how does the displacement vary in between these 3 nodes in this element? So like linearly is the simplest one, linear shape functions. They just mean they vary linearly. And why it does that is, well, it integrates this equation. So to replace integrals with numbers at points, we need to make some assumptions about how displacements vary, things like that. So when it does that, if it's assuming it's very linear across that, the real underlying displacement may actually vary in some complicated manner. So that simplifying assumption introduces an error, and that error is called discretization. Discretization because you're discretizing the geometry or equations, which means splitting them up into little bits. And so that introduces a type of numerical, and that tends to get smaller as you reduce them. Sorry. One has died. I just want to check the thing. Oh, sorry. Can you go back to that? So in this case, for this equation, we have 7 nodes and each has 3 unknown scalars. So that's 21 scalar unknowns and we have 3 equations. But if I just go and apply that same method to every node in this mesh, then if there are 1000 nodes, each with 3 unknowns, and I apply that same 3 equation method to each node, then I'll get the same number of equations as unknowns. And they'll all be coupled. So for this node up here, it will have these 4 points in it. If I take the next one over, it will share some points, but then have some other points. So if you imagine a big bunch of simultaneous equations, and you say the unknowns are x1, x2, x3, x4 up to x,000, and some equations will have numbers x1 to x3, some of them will have like x3 to x7, some of them will have like nx15 and x1000. So some of the equations will share the whole way, and all the unknowns will appear in at least one equation. So once you set all that up, you can solve that system. So you'll get a big bunch of simultaneous equations, and then you can write that in a matrix form. So if you simultaneous equations, you can write that in a matrix form, which I'm calling K here, and then U are your unknown displacement vectors, and anything on the right hand side you call F. So that's where linear algebra comes in. So it's just manipulating these large systems of algebraic simultaneous equations. So if you have something that looks like this, then if you've done a maths course in linear algebra, you would have talked about how do you solve simultaneous equations using matrix space. So in this case, we can comment on something. So this K matrix, so it's a sparse matrix. Sparse just means it's mostly zeros. If I have this giant matrix, each equation only has like 7 nodes in it. It doesn't mention all 1000 displacements. So it's just like 7 non-zeros in any row, or depending on how many nodes there are. So that means it's mostly zeros. And then U is the unknown. So if we have n nodes, 1000 nodes, then this matrix would be 3000 by 3000 because of 3 unknowns. 3 unknowns. And then if in the linear algebra course, when you covered how to solve simultaneous equations in matrix form, you just multiply by the inverse of this matrix on the left and right. So you'll have K inverse here, that cancels out, and then you K inverse on the right hand side. Okay. So typically when you press submit and run, the slowest part is it doing this. It's just trying to solve these equations. It's just inverting this matrix. It normally doesn't directly calculate this K. There are methods where you can just calculate this whole right hand side without directly calculating the storing K. So there's methods known as Gaussian elimination, which is essentially what abacus does, or LDU decomposition. So they're very similar methods. So when you solve simultaneous equations in matrices by hand, that's probably what you do. So U here are called the primary unknowns, or the primary solution variables. So that means once you solve those, then you know everything. So you can calculate strain and stress once you know the displacements in every mode. So that is it. I know that was probably heavy going at times, but hopefully through the next sets of lecture slides, and I'll upload other bits of content online, that you'll hopefully by the end of the module be able to connect the underlying theory with when you press go, what actually happens, and when you specify identification, what actually happens. But okay, that's it. So thanks very much. I know a Friday afternoon is not always the best, most energetic slot for a lecture. But if you have any questions, just come up to me afterwards. Thanks.